Oxidation numbers are a method to track the transfer of electrons within a chemical reaction. Something to kind of consider is that some people consider oxidation numbers to be the charge that an ion or that an element would have if it were in that compound but acting as an ion on its own. It's a little bit tricky to kind of try to dive deep into what these oxidation numbers are truly representing. But the easiest way to handle them is to just think of them as a bookkeeping method of how we're going to keep track of whether electrons are flowing one direction or another. But in order to use these oxidation numbers, we have to be able to identify what an element's oxidation number is, and there's a set of rules that will help us do that. So these rules for oxidation numbers begin pretty straightforward. If it's an element by itself, such as sodium, oxygen, sulfur, it doesn't matter whether it's monatomic or diatomic. If it's an element by itself, the oxidation number for that element will be 0. The next couple rules focus on specific elements. The second rule talks about hydrogen. Hydrogen has an oxidation number of +1 unless it's acting as an anion, which will of course mean it's bonded to a metal. Then it will have an oxidation number of -1. So hydrogen is almost always a +1 oxidation number when in a compound unless it's attached to a metal. So if we had something like NH3, then we would know that since this is not attached to a metal, that this hydrogen has a +1 oxidation number. But if it were something like NaH, where I can clearly see that this hydrogen is attached to sodium, which is a metal, then in this case this hydrogen would have a -1 oxidation number. Our third rule addresses oxygen. Oxygen is always going to be a +2 oxidation number, except in one specific circumstance, and that's when it is bonded inside of a peroxide, which is simply something to O2. For example, you've probably heard of hydrogen peroxide, which is H2O2, or maybe sodium peroxide, which would be Na2O2. In these cases of these peroxides, the oxygen would have a -1 oxidation number, which I didn't actually write here, so let's do that now. Unless it's in a peroxide, then it's -1. Oh goodness, I said +2. Let's correct that right now. My apologies, oxygen is -2. Oxygen is -2 unless it's in a peroxide, then it will have a -1 oxidation number. Sorry about that. Number 4, monatomic ions have an oxidation number equal to their charge. So if you had sodium, which has a 1+ charge, then its oxidation number is +1. If you had calcium, which has a 2+ charge, its oxidation number is +2. And that works true for the anions as well. If you had oxygen with a 2- charge, then it would have a -2 oxidation number, which makes sense because oxygen should anyway. Or something like phosphorus with a 3- charge, that would have an oxidation number of -3. Rule 5 says the sum of the oxidation numbers within a compound is 0. So let's go back to an example we had just a moment ago. This is going to be one of the most important rules because it's going to help us determine the oxidation number of all the elements that we don't have rules for. So like in the case of NH3, we know that hydrogen here is either +1 or -1, and since it's not bonded to a metal, this hydrogen is going to have a +1 oxidation number. Each hydrogen within this compound has that same 1+ oxidation number. But the sum of all of the oxidation numbers in this compound has to be 0. So really you have a nitrogen, a hydrogen, another hydrogen, and another hydrogen. Each one of these hydrogens has an oxidation number of +1, so in order to cancel out and be 0, this nitrogen must have an oxidation number of -3. Well, the same can be said about polyatomic ions. The oxidation numbers within a polyatomic ion have to add up to equal the charge of that polyatomic ion. So if you had the polyatomic ion sulfate, which is SO4 with a 2- charge, we know from our previous rules that this oxygen has an oxidation state of -2. However, just like a second ago, there's really 4 oxygens within this SO4 polyatomic ion, And we know that each one of these oxygens has a -2 oxidation number. However, whatever sulfur is, when we add that to all of these oxidation numbers, has to equal the charge of this sulfate, which is -2. So we have sulfur's oxidation number, which we don't know, plus the combined -8 oxidation numbers of the oxygens. And if you need to do a little algebra, you can, but we're just going to add 8 to both sides. This means this sulfur has to have an oxidation number of +6. So then let's go back and think about it just to make sure that works. We have SO4 with a 2- charge. So we have sulfur, which was +6, an oxygen, which is -2, another oxygen, which is -2, and 2 more oxygens, which are -2. When you add these together, they do indeed equal -2, which matches the charge of the polyatomic ion. So here is a page where we can practice, and we might not do all of these, and we'll go kind of quickly on them, so feel free to pause or slow down the video. But we'll start with Cl2. Well, that's just chlorine in its elemental form, so it's going to have an oxidation number of 0. Whereas Cl minus, the chloride ion, is a monatomic ion with a 1- charge, so its oxidation number will be -1. Next, sodium. Again, that's just sodium all by itself, so it's going to have an oxidation number of 0. The next one is a sodium with a 1+ charge, so its oxidation number will match that of +1. Next is oxygen, just in its elemental form, so we know it's 0. Same here with number 6, nitrogen. In its elemental form, oxidation number 0. Number 7, really this is a typo, it should say Al3+, not +3. But this aluminum 3+ ion has a charge of 3+, so it will have an oxidation number of +3. Now when we get to these bottom ones where we're trying to assign oxidation numbers within a compound, we can just filter through our rules. We see hydrogen, which is not attached to a metal, so we know hydrogen will be +1. However, there are 2 hydrogens here, so that's 2 +1s that have to cancel out to equal 0 since this is just a compound. Well, that means that the oxygen must be -2 because a +1 and a +1 and a -2 will sum up to be 0. Plus, we should have known from our rules that we have oxygen here, and oxygen's always -2 unless it's in a peroxide. On number 9, we have NO3 with a 1- charge. We know that oxygen from our rules is -2, so that's 3 -2s for a total of -6. However, they have to equal a -1 because of the 1- charge of this. So what number plus -6 equals -1? Well, that means this nitrogen would be +5. On number 10, it's very similar. Oxygen's number -2, and since there's 2 oxygens here, that's a total of -4 from the oxygens. So the nitrogen must be +4. Now number 11, again, we see oxygen here, so it's got to be -2, but this one's worth taking a bigger look at. It's Cr2O7 with a 2- charge. Now this oxygen we know is -2, but there's 7 of them, so that's really a total of -14 oxidation states. We need only -2 of those to be left, so that means these chromiums have to be chipping in +12 because 12 minus 14 is -2. Well, since it took 2 chromiums to net this +12, each one, because we're going to break this in half, must be a +6 oxidation number. So we can kind of think a little bit further on this, make sure it works. We have chromium, which is a +6, chromium, which is a +6, and then 7 -2s, 1, 2, 3, 4, 5, 6, 7. And when you add those together, they should equal -2, and they do. For number 12, this is just an ionic compound, so we can just say that the oxidation numbers are going to match the charges. Chlorine's got a +1, or potassium's got a +1, and chlorine's got a -1. 13 we actually just did on a previous page, but hydrogen's +1. Since there's 3 hydrogens, that nitrogen has to cancel them all out to be -3. On number 14, we have hydrogen, but this time hydrogen is attached to a metal. This is acting as an anion, so this hydrogen will have a -1 oxidation number. Since there's 2 of them, that calcium would need to be 2+, which makes sense because calcium makes a 2+ ion. Number 15, oxygen again is -2. There's 4 oxygens present for a total of -8. We need all but 2 of those to be canceled out, so sulfur must be a +6. On number 16, we have Na2O2, so that is a peroxide because it's following the something 2 O2 pattern. So in this case, oxygen's a -1 oxidation number, and sodium would have to cancel it out to be a +1. Okay, so here are the next few, just to save you some time if you wanted to go back and try those on your own. Just rewind the video a bit. But I do want to talk about a couple of these ones down at the bottom because they're a little bit harder to think about. You can really break these down into, for example, H2SO4. You can break that down into the hydrogen and the sulfate polyatomic ion, or you can choose to think of the compound as a whole. It doesn't really matter. Either way, though, we're going to start here with the oxygen. We know oxygen's -2, and we know hydrogen is +1. Well, that's really 2 +1s and 4 -2s. So this H is a total of +2. Now, really, when we answer, though, we think of the individual ones, but these H's are totaling +2. The O's are totaling -8. Well, that means whatever sulfur is has to cancel out the difference because this compound has to net be neutral. So what's going to cancel out +2 and -8? Well, that means sulfur would have to be +6 to make the sum of these be 0. So each hydrogen has an oxidation number of +1. The sulfur has an oxidation number of +6, and each oxygen would have a -2 oxidation state. So I'm going to go ahead and fill in the rest of these 27 through 30. If you want to work them on your own, make sure to pause the video before I fill them out. And there are the rest of them. Okay, so why is this important? Well, in chemistry, there are a type of reaction called oxidation reduction reactions, which are commonly called redox reactions. In order for a redox reaction to occur, there has to be a process called oxidation, but oxidation can only occur if the process of reduction occurs. So what are these? Well, oxidation is the loss of an electron in the process of a chemical reaction. Losing this electron is actually going to increase the oxidation number of that element. And that makes sense. If you think about it, you're losing a negative charge, and losing a negative charge would net you to be more positive. Reduction is the gaining of electrons, and this will reduce the oxidation number of the element because you're gaining something negative, so that's going to bring your oxidation number down. A fun little way to remember this is Leo, who's a lion, of course, says grr. And this is just a silly mnemonic device for losing electrons means oxidation, and gaining electrons means reduction. So how this applies, if we look at some chemical equations, we can actually assign all the elements on the left side of a chemical equation and all the elements on the right side of a chemical equation their oxidation numbers, and then we can analyze those oxidation numbers to see if any of them changed. Because if any of those oxidation numbers changed throughout this process, then that indicates to us that there was a transfer of electrons, and that we then know that an oxidation reduction reaction took place. So let's look at A. I guess we should balance it first. Put 2 there. All right, it's balanced. Looking at this hydrogen, he has an oxidation number of +1. Chlorine's got an oxidation number of -1. Zinc is an element by itself, so he has an oxidation number of 0. Hydrogen, oxidation number of 0, since he's an element by himself on the right side. Chlorine and zinc It's an ionic compound, so we can just think of their charges. Chlorine's got a 1- charge, so it has a -1 oxidation number, which means zinc must be +2. So if we look and see if any of these change, right off the bat I can see hydrogen went from a +1 to a 0 oxidation number, and zinc went from a 0 oxidation number, let me change colors, a 0 oxidation number to a +2 oxidation number. So since there was a change in oxidation number, we can conclude that this is indeed a redox reaction, but we can take it a step further. Let's think about the zinc here. Zinc went from an oxidation number of 0 to an oxidation number of 2. That means that zinc lost 2 electrons. Zinc was oxidized. Hydrogen, on the other hand, went from a +1 to a 0. His oxidation number was reduced, so we know that hydrogen in this reaction was reduced. You can't have an oxidation-reduction reaction without both parts happening. So if something is oxidized, something has to be reduced with it. So let's try the next one. Looks like we need to balance it. Putting a 2 here. Oops, that's not a very good 2. 2 there. 3 here. 2 there. 3 there. And then let's just go through and assign oxidation numbers again. So we have copper and chlorine, an ionic compound. So just worry about their charges. The oxidation numbers will match them. Chlorine's got a -1 charge, so it's got, or a 1- charge, so it'll have a -1 oxidation number. Copper in this case will have a +2 oxidation number. Aluminum's will be 0 since it's by itself in its elemental form. Same for copper on the right. Chlorine still has a -1, and aluminum must be +3 to cancel them all out. So let's look and see if anything changed. I see that copper's went from +2 to 0, and aluminum's went from 0 to +3. So yes, this is a redox reaction. And I see that aluminum went from 0 to a +3 oxidation state. That means he lost 3 electrons. So the oxidized component here was the aluminum. And the reduced would be the copper, whose oxidation number dropped from +2 to 0. For the next one, we can balance it too. Okay, sodium has an oxidation number of 0. He's by himself. Chlorine by himself. On the right side, they'll just match the charges, so +1, -1. And I can see that sodium lost an electron, so he was oxidized. Chlorine gained the electron, so he was reduced here. So pause the video, try these next 3 on your own, and I'll give you the answers in just a moment. All right, so here are our answers. Of course, I didn't balance this last equation. Let me fix that. Okay, and so with that mistake that I just made, you can notice that you don't actually have to have the chemical equation balanced with coefficients in order to determine whether it's an oxidation-reduction reaction and to determine which one was oxidized or reduced. So in this first one, we've got magnesium being oxidized and hydrogen being reduced. In the next one, we have iron being oxidized and oxygen being reduced. You can see that from iron's oxidation number increasing and oxygen's decreasing. And in the last one, magnesium is the oxidized species and aluminum is the reduced species.